So maybe before we start, I would like to make one very short general announcement. We created in Slack a channel for positions announcements. And this is the place where all of the professors can post their advertisement for PhD, postdoc, faculty positions, and where the students can find interesting information about what is open for themselves or for their colleagues and friends. So maybe I just write it in the Zoom. Feel free to go on Slack. Positions.
Also, there is a channel for feedback, right? And there is anonymous capability, so maybe you can mention that as well.
Yes, we also thank you, Oleg, for reminding me. We created a channel called RV Feedback to SC, and this is where you can give any kind of feedback that you would like to the steering committee about what you think can be improved about the conference, about diversity. So any kind of feedback that you would like to share to the steering committee, and you can also write anonymously to this channel. So when you open the channel, there is a short description how to do it anonymously.
Okay, so I think we should start.
Absolutely.
Okay, so first of all, my name is Ezio Bartocci. I work at TU Vienna, and I'm the session chair for this invited talk of Katherine. We have the pleasure to have here with us Katherine Driggs-Campbell from University of Illinois at Urbana-Champaign. Just let me give you some background about her. She's currently an assistant professor at University of Illinois Urbana-Champaign at the Department of Electrical and Computer Engineering. She was a postdoc at Stanford in the Intelligent Systems Laboratory, and she received the Bachelor of Science with honors from Arizona State University in 2012, and the Master of Science at Berkeley, UC Berkeley in 2015. Her main work is on human-centered autonomy, focusing on integration of autonomy into human domain fields, merging ideas from robotics, learning, human factors, and control. The title of the talk that she's going to give us is Fantastic Failures and Where to Find Them, Design Trustworthy Autonomy. And before giving the stage to her, just let me remind what is the protocol for the question. At the end of the talk, you can make question either by using the Slack channel and writing the question on the channel dedicated to Katherine, or the other possibility is to raise the hands using Zoom. And now I give the stage to Katherine. Thank you.
Great. Well, thank you so much for that introduction. I'm very excited to be here and to talk about some of my work in autonomous systems. Today I'll be presenting work mostly done by two of my students, Peter Du and Tianchen Ji. I'll also be presenting some work by my collaborators at Stanford in Michael Kokendorfer's lab, and as well as here at Illinois in Girish Chowdhury's lab and Cheyenne Mitra's. So to give a little bit of context about my group and how I approach things, I generally look at how we can design safe autonomous systems that need to operate out in the real world with people. So I am a practitioner of autonomous systems. So today, instead of talking about some of the things that worked really well, we'll actually be highlighting some of the failure cases and really thinking about the cases where it didn't work out so well. So hopefully this will be of interest to all of you all, and hopefully we'll start getting some insight about how we can really look at these failures or cases where things didn't work and really think about how we can connect this to assessing safety and using these insights to in turn improve performance. So we'll be talking about all these failure cases and then touching on how we actually fix some of them. Okay, so when we talk about robustness or failures, one thing that I've found sort of interesting is that when you start looking at the application or deployment of these systems, the context becomes very important. And depending on what sort of application you're looking at, you'll require different representations and priorities. So for example, in my lab, we look at many different applications. Here is a sampling of 3. So we look at things like agriculture or field robots, transportation and autonomous vehicles, and we have some work in manufacturing as well. So I think one thing that's sort of interesting to note about all these different applications is even though they are quite different, and one of the things we can start doing to kind of connect these different applications is start thinking about the structure or what is sort of inherent in these systems. And if you'll allow me to make some sort of sweeping generalizations, one thing we can start to think about is how through these different applications, we have this idea or notion of increasing structure. And I don't have a strict definition for what this structure means, but basically we have very different models and assumptions that we can make about these different systems. So to explain that a little bit more, in the, say, manufacturing context, we have a lot of control over the whole environment. The processes are very well defined, and we're basically free to introduce new assumptions. It's a very well-defined, controlled environment. If we move to transportation, we have cases where there are very clearly defined rules of the road. For the most part, we can define what a failure is, but there are many scenarios that become fairly unstructured through interactions with other agents or when we have some assumptions that are violated. And if we go to the far end where we have this agricultural or field robot, this is a case where we really have very difficult environment that we have to operate in. So the world around our system is constantly changing. Something that I learned moving to Illinois is you can actually hear corn growing. So it grows very fast. It's changing all the time. And there are many simple assumptions or systems that you often think you can rely on that actually sort of break down. So for example, if you want to have a good state estimation, in the case of these robots that are out in the field, you actually don't have access to things like GPS. So it's very difficult to even know where you are in the world. So when you look at this far end, the failures that you encounter or the uncertainties that occur are often very difficult to characterize. And so as we think about these different applications and think about the different failures or how we want to design these robust systems, just keeping in mind these different structures and what we have available to us through the application, I think is something that's good to keep in mind as we go. So today we'll be mostly talking about the transportation domain. So we'll be talking about some of our efforts and failures in autonomous vehicles. And then we'll talk about some work in field robotics in the agricultural domain as well. So specifically, we'll be looking at different classes of failures. So we'll start with talking about some of our real world experiences when we're trying to develop our systems and thinking about deploying them on public roads. We'll then move to simulation cases. So thinking about how we can find failures and find different failures that we aren't able to capture in the real world in simulation. And then we'll talk about, again, the ag case where we have these failure cases where we can't really define them and we have to sort of view them as anomalies. All right, so we'll jump in. So we'll start with a discussion of our real world tests here. So I'm going to be talking about some of our work. So this was work that I did throughout my PhD, my postdoc at Stanford, and this was sponsored by SAIC. So in this project, we were looking at how we can design data-driven or learning-based systems that operated safely out in urban settings. So we were basically working on this full pipeline of the autonomous stack, going all the way from perception or taking the input from perception and working on the decision-making and control. And again, our goal was basically to help to design a system that was safe and effective. effective. So again, instead of talking about sort of the cool demo at the end, which at the end of the day is actually quite boring because safe driving is not that exciting. We'll talk about our failure cases. So we're going to talk about our interventions, or some of our interventions. So an intervention is when we are in autonomous driving mode and our safety driver has to take over in an unplanned fashion. So this is when something, some failure case is about to happen, but the human takes over. Okay. So this first one is a case where we were working on a lane changing system. So here you can see this is the front view of our camera. Here's the sort of the sensor display of the vehicle itself. It's going to make a lane change, and at some point it's just going to start sort of veering towards this agent, and we intervene and stop here. So this was a failure that was caused by model mismatch. So there were a few, or at least partially caused by model mismatch. So there are a few issues that popped up here. So first, basically what the vehicle was trying to do is it's trying to merge behind this agent here. But the model that we were optimizing online was notably different from the actual vehicle. So basically the internal system thought it was able to make this change safely when the car actually wasn't able to. Another influence of this was we actually had a sort of conflicting objectives points where the car was both trying to be efficient, so it wanted to overtake this vehicle so it could maintain some speed, but also realized it needed to make a right turn soon, so it needed to go back to the other lane. So there are a few sort of things that caused this issue to happen, but we believe the primary cause was this idea of model mismatch. So basically the simulated system or the internal system didn't match the actual one precisely. Okay, this next one, hopefully you can see it here, but here we're trying to navigate this intersection. You'll see we have these detection boxes here for these cars that are coming in and out. So we're basically trying to track and understand when we can navigate this intersection effectively. You'll also note that the camera is a little washed out with the sun. But basically we're in this point where we were basically frozen for a long time and we took over so we could actually go through the intersection. So in this case, the problem was we didn't have a good model or understanding of the perception uncertainty. So the types of tracking failures that happened in the perception system were not well represented. And we actually had a very hard time connecting these outputs from our perception to our decision-making and control system, which was sort of the ultimate points in what we were trying to design. Okay. And this last one, this one is on a more recent car. And this one, it's a little bit harder to see. But if you, let's see, if we track the wheels here, one thing you'll notice, we're trying to follow a curve here. And we'll see that at some point the wheels straighten out and we start sort of going straight towards the wall, and unfortunately right to where all the students are standing. And so this was a case where actually the localization system failed. So there was something about this corner of the room and it became very hard for us to localize ourselves, and we thought the track was somewhere else. So these are sorts of problems that we encountered when we were designing and deploying or starting to deploy our systems. So now the question is, okay, we've encountered these failures, and I will say it's, or emphasize that it is a good thing to find these failures so we can fix them. So the question is now, how do we take these failure cases into account, and what should we do sort of downstream to take these issues or causes into account? Okay, so if we were to take a sort of robust decision-making or control stance, we can fall back on some traditional methods to basically optimize our controller or to fine-tune our controller to have this robust system. So if we wanted to cast this in the traditional sense, we can formulate this problem, basically saying we want to efficiently and safely control a vehicle, and we want to take into account these sorts of uncertainties and disturbances. So we can have our dynamical equation here. So we have the dynamics of our system denoted by F. We are trying to find our controller. So these are going to be our inputs to our system. So this is going to be basically what we use to navigate or control or do whatever task we're trying to achieve at the time. And then we can try and capture the uncertainties and disturbances as this function that gets added to the dynamics here. So this function can be, or this can be a function of our state, our input, as well as some uncertainty or noise. So this is a very traditional formulation, and this has been, something that's studied by the control community for many, many years. And some of the original motivations for this was really thinking about how we can look at things like sensor uncertainty or sensor noise and environment uncertainty. So this is very good at handling some unknown parameters or something like Gaussian noise on your system. Again, where we can think about this idea of additive noise, and we can basically try and bound this and protect against the worst case. So basically what we want to do is try to control or stabilize our system and not violate some constraints here. And as you implement these controllers, hopefully you have a good understanding of what these disturbances could be, and you can start taking them into account. We can also take this additive component and try and characterize model mismatch, or we can think about this as trying to capture some unmodeled phenomenon. So again, this is something that in the sort of traditional control side of things is an important concept, because usually we have some model that we have specified or learned or identified, but there are always going to be some unmodeled phenomenon or some nonlinearities that we can't quite capture. So building on that sort of old saying that no model is perfect. So we can also take these this bit of sort of additional model uncertainty. We can also add that here. And you can capture this in robust control frameworks as well. This has become increasingly important now that learning-based control has sort of taken off as well, because this is basically a case where we can now start thinking about the cases where our system is trained in simulation that can be very different from our actual deployment case. So there might be some situations that are not well modeled or well represented, or something about the dynamics might not be perfect in simulation. So again, this is something that is captured in the old control frameworks, but increasingly important from the learning perspective. And this takes a number of different names, like domain transfer, sim to real, and robust learning in general. So to maybe highlight that, so here's a quick video where we were trying to basically just test and see how end-to-end learning systems would work on the vehicle. So here we have our sensor view of the vehicle itself. This is our front view here. And this is a visualization of what is going on. So here, this agent here is going to be our ego agent. So this is the one that we are controlling. And we have a series of obstacles. So you'll note we have them visualized here, but we are actually spoofing our sensors. So these agents aren't here. You'll notice in the vehicle there, or from the vehicle view, that there are cones that you'll be able to see, but you'll see why we didn't want real cars there in a moment. But again, so we wanted to test out some of these end-to-end learning systems and basically see how these work in practice here. Okay, so here's our vehicle. We are controlling it, and we're doing this weaving maneuver here. So what you'll notice is we start observing this phenomenon where we have this sort of cascading or compounding errors, and it's basically an unstable system at the end of the day. So because of the mismatch between the data set and the real vehicle, you often have these cases where as you start running for longer and longer times, your errors basically accumulate and you start performing worse and worse. And there are different ways you can handle this. So one, you can fix it from the data side. So you can think about how you can collect more data and start taking into account the fact that you won't get perfect coverage of all the states, but you can try and collect more data or actively search the space to try and fill in these gaps. The other alternative is you can start thinking about how you can improve your simulation. And one of the common approaches is to take a robust adversarial approach. So if you can start thinking about where your uncertainties come into play, or start thinking about basically where you should be adding or changing these noises and uncertainty, you can basically start adding this into your simulation environment, or cast this as, say, a two-player game, where you can start basically training your system in a adversarial environment. And the idea is if you are capturing these uncertainties or these aggressive or adversarial settings, you should be more robust and effective in deployment. And I think one thing that's important to note about these systems is, so that this is a good approach often when you are going from simulation to real world or you're trying to capture these mismatches, but there is no free lunch, so to speak. So this red example or this red line here is our case where we were implementing these robust learning systems. And as we increase basically the adversarial environment, so as it gets more and more adversarial, and hopefully capturing some of the mismatches more aggressively, we can see that we tend to have more consistent performance, whereas many other methods start falling off and decreasing in performance. But the important thing to note here is that if we think about basically the reward or the performance, we do sort of sacrifice some peak performance. So there is no free lunch. You are going to have more conservative behavior as you're starting to look at these cases. Okay, so basically these approaches hopefully start capturing some of the failures that we saw and started kind of capturing some of these uncertainties. But one thing that's important to note is the failures that we saw earlier on probably don't really capture the failures that we think of when we're actually deploying systems, or failures that we see or that we think of like collision-wise with agents. So a lot of these methods and a lot of these approaches are very good at handling, again, the cases where we can think about basically how to model these disturbances or these failures as just an additive noise, but it doesn't really capture things like long-term interaction or some of these sort of other weirder cases that can't necessarily be described this way. So to help capture these other failures, this is often where we turn to simulation. So now we're going to talk about some other work or related work where we're thinking about how we can find failures or identify likely failure cases in a simulated setting. So for a little bit of motivation for the simulation case, and I know I am preaching to the choir here, but one of these sort of interesting phenomenon about autonomous vehicles and many safety critical systems is our events of interest or high risk events are also low probability. So it's often not trivial to identify these collision cases if you have a relatively solid system. So again, as sort of a motivation for this, if we look at these last two lines here, these are the collision and fatality rates for human drivers. So this is basically how frequently human drivers get into a collision or get in a collision that causes a fatality. And so we can see that this rate is actually pretty good. So we have actually a very low collision and fatality rate. And I think it's always really important to remember that humans are actually very good at driving, right? And so if we wanted to start thinking about showing that autonomous vehicles are just as good or better than human drivers, if we wanted to try and do this, we would basically have to get at least an order of magnitude more kilometers driven to start getting a statistically significant sample of these failures. And perhaps not as relevant, this top line here is the disengagement rate. So this is the rate of interventions, and this is about 2 years old, so it's a little bit out of date. But this is basically when the companies that were testing their vehicles on road or public road testing, how frequently they went from autonomous mode to a human-driven mode in an unplanned fashion. And we can see that this rate is significantly higher than these collision rates. So even though collisions didn't actually occur, these interventions were happening fairly significantly or at a very high rate. Okay, so but back to the idea of trying to find these failures on road. If we really wanted to try and get a good sampling or get good coverage, we would have to have a huge investment in public road deployments. So this has significant economic costs, both because collisions in the real world are very costly, but also just in terms of the hardware investment itself. So to help compensate for the fact that this is not really feasible at scale, we can start turning to simulation and start thinking about how we can run simulations to help compensate or understand our failures before we hit deployment on the road. In these simulation cases, I think one thing that's important to note here is that the simulations, it's much more cost effective than real world deployments, but it still comes at a fairly high cost. You can throw as much compute as you want at it, but it's not obvious that this is going to be put to good use. So what we want to do is we want to start thinking about how we can efficiently use simulation to find these failure cases or find events of interest. One of my favorite sayings that I think is relevant for this is everything in simulation is doomed to succeed. So we want to make sure that we are not just always succeeding and sort of justifying ourselves. We want to make sure that we are actually capturing the important cases. So I know this is something that you all think about a fair amount, but just to sort of motivate why this problem is hard in simulation too. And if we wanted to take even a relatively simple system like a vehicle, so let's say this is our autonomous vehicle. So let's say we are given the full stack that we want to test and validate. And we want to see basically how it interacts or see if there are any safety concerns when it's approaching a crosswalk with a pedestrian. So if we start thinking about how to test this sort of system, if we wanted to say discretize the motion or do some sampling-based model, depending on what model is guiding this pedestrian, there's a good chance we won't actually get good coverage or really capture the interesting cases. So if we expand our model or maybe expand where we are trying to explore and sample, we can basically get more trajectories and more things we need to explore. But it's not exactly obvious which of these are useful or which ones are likely. And as we start sort of building up in complexity and really thinking about deploying this on the road, things become much more difficult. So if we were to add other agents, we have this sort of combinatorial complexity that starts growing. And we can also think about capturing these sort of weird trajectories that maybe a person would do, but it's not obvious whether or not these are actually useful. So really what we want to do is we want to be able to find a system that can help us efficiently and effectively basically explore this space and find things like the most likely failures. So we don't have to basically explore everything. We just want the things that will lead to a failure and are likely to happen. So to do this, we've been working with a tool and an approach called adaptive stress testing. And basically what this does is this is going to help us try and come up with a way to efficiently explore the simulation space and find this not quite fully adversarial, but basically find these disturbances or things in our system that will cause failures. And the key insight for this, this approach is that we're going to actually use new insights or advances in reinforcement learning solvers to help us actively search the simulation space. So if we have a simulator that both captures our agent as well as the environment, what we're going to do is we're going to use these RL solvers to basically help us control the environment and try and find the cases where the system will fail. And basically, as we are searching the environment, what we need to tune is this reward function. So basically what this is going to do is we're going to try and have our solver find failure cases. So we're going to basically penalize it for not finding some failures. And we're also going to add this other piece where we are trying to incentivize it to find likely failures. So depending on how much access and information we can get from our simulator itself, we can actually understand how likely different actions are depending on what is available in the model itself. So basically what this is going to do is this is going to help us return example cases where we have failures and not only failures, but failures that are also likely given the underlying models and things in our simulation as well. And I think an important thing to note here is this is not necessarily a method that gives good coverage, and it doesn't necessarily guarantee, or it's not necessarily guaranteed to find a failure. But as with a lot of reinforcement learning approaches, we do have pretty good odds of finding a good failure. And depending on how much transparency you want, you can use different types of solvers that have more or less guarantees. So you can have something like Monte Carlo tree search, which is fairly interpretable. It gives you good control over what you are exploring. Or you can go to something that scales very well, like the deep learning approaches, or deep RL, where you can scale to very complex systems, but it often takes a little bit more work to actually find the failures itself. Okay, so let's lean into this example a little bit more and think about this case where we have a multi-agent crosswalk example. So here we have our ego agent, and again, a pedestrian here with some noisy detection as well here. So if we were to open up our simulator a little bit here, we will assume we have some access to different parts of the simulation. So our testing solver is basically going to control our pedestrian or participant dynamics. So we're basically going to be controlling this agent as well as noise on our sensor modules. So this will again help us basically try and find these cases or these trajectory examples where a system is likely to fail. Okay, so basically by iteratively probing the system, we can start gathering these examples and hopefully guide our system to failure. I would like to note that this is also fairly similar to statistical model checking. So you can actually think of this as being fairly related to things like Monte Carlo sampling, where you can get a risk estimate throughout a full trajectory. And this can actually go into your reward function here. Another thing I forgot to note is one of the nice things about having this sort of as a reward function that you can tune is it's fairly easy to add some other heuristics or other incentives to your system. So you can start to sort of easily tuning where you want to search or what types of failures you want to find, since the reward function is something that's fairly easy to tune. Okay, so as I mentioned, if we were just to run a collection of simulations, we would often using just normal methods and normal simulations, we would often just be sampling from the most likely cases, and we'd get fairly typical or well-behaved simulations. Okay, so again, this is something that if we continue to sample, we probably wouldn't get anything meaningful out. Okay, now if we go to the other extreme where we just wanted to find any failure, we would get something like a worst case or an adversarial example. So we'd get something that looks like this, where we sort of just have this pedestrian that just runs into our system. Now, the problem with this is also not that useful. As I mentioned before, if we're just looking at these sort of worst case or adversarial scenarios, we're probably not going to actually get anything meaningful out, especially in this case, in this example, our agent itself is actually performing everything right. It is coming to a stop. It is not at fault. So this also is not sort of useful. We want to be able to find these situations that are meaningful and that we can actually address. So one of the big questions is how do we actually take this and find relevant failures? So we want to be able to sort of more concretely identify where sort of the sensitivities are in our system and sort of guide it there. And that comes basically down to figuring out what the best searching method is and figuring out if there are basically ways we can guide our reward function to finding something that is, again, relevant. Okay, now, so here's a sequence of failures of different types and cases. So again, if we are now, thinking back about what we're supposed to do with these failures, because at the end of the day, we want to take these failures, use them as insights so we can design our safe autonomous systems. So one thing you can do is if you can find these key failures, you can basically loop this back into something like the robust or adversarial learning, or use this to just fine tune your policy. So you can basically take these cases and loop it back. Another thing that we've observed is one of, at least in this scenario specifically, is often one of the key problems is having a good understanding of what the pedestrian is going to do and making sure you take that into account in the autonomous system stack. So one of the more recent projects that we've been working on is actually connecting some of our work in autonomous system design and pedestrian intent estimation and connecting this with online monitoring through reachability. Okay, so if we have a situation that is fairly similar to what we were just observing here, where we have a pedestrian and it is going to be guided or motivated to move according to some underlying intentions or goals. And then we have our agent, which is trying to basically navigate safely through this scenario. So we wanted to test this system out, and we've been working with this we'll call it a smart car, not a golf cart. This smart car that has been provided by Autonomous Stuff. So we can build up this whole autonomous stack and see if we can start now having safer, more guaranteed interactions with pedestrians. So this means that we need to build up the pedestrian intent and integrate this intent estimation and trajectory generation, incorporate this into our autonomous stack. And we've also been working with Cheyenne Mitra, as I mentioned before, and using his tool for driver or C2E2 to give us some reachability analysis so we can understand if there's going to be a likely collision and make sure that we have some guarantees in what's going to happen down the road. So again, we can combine this all together, and so we can have something like safe and guaranteed interactions on the road. Okay, I will admit that this video is not the most exciting video in the whole world, but that is me walking in front of the moving vehicle. And I can't think of a better way to show how much I trust my students other than just walking in front of a moving vehicle for them. Okay, so we can build up this full system and have some semblance of guaranteed and safe interaction with these agents. And again, to stay sort of true to the theme of this talk, this is an example of it working exactly the way we want it to, but this is not always the case. There are situations where the failure isn't necessarily a failure in the sort of traditional sense, but there's the case where the vehicle just never moves. And one of the big challenges is trying to figure out how you want to tune how conservative your system is, because you might not get a safety risk, but you're also not achieving anything in terms of efficiency or having an effective system. So figuring out the right balance here is tricky. And we also get cases where there is some failure in some other situation where the vehicle just doesn't stop. I don't know if that video is playing very well. Let's see if it'll replay correctly this time. Yeah, so sometimes we have the case where it just doesn't stop. But once everything is tuned and works effectively, hopefully we have something that works with guarantees as expected. All right, so this is basically all I have to say at the moment for some of this work in autonomous vehicles. So now we're going to switch gears and start talking a little bit more about a case where we have significantly less structure in our system and thinking about where we don't necessarily have well-defined failures, but we have these anomalous cases that we need to address. Okay, so to get just a little bit of motivation, I think often when we think about autonomy, it's very easy to think about the autonomous vehicle case. Because autonomous vehicles are something that we, or driving in general, is something that we all have experience with. And this is something that sort of makes sense to all of us. But we can also think about sort of autonomy in other cases, like agriculture. So agriculture is actually a very interesting case, in my opinion, because it often doesn't sort of seem as safety critical or as impactful as something like mobility and transportation as sort of we view it. But if we think about the sort of future of our food systems, it's also very critically important. And often when you think about, if I were to tell you about autonomy or autonomous systems in the ag case, you'd probably start thinking of relatively big tractors or sort of these big systems that go over whole fields. But one of the things that we are trying to move towards is thinking about how we can avoid some of these really large, heavy, expensive equipments and think about smaller, more agile agbots. So the idea to moving to these smaller systems is that we can start improving this idea or moving towards more precision agriculture. So we can basically reduce some of the negative impacts of these larger systems and start thinking about how we can basically be more specific and more catered to the systems themselves. So we're working on these small agricultural robots or agbots that basically go beneath the canopy. So they are less detrimental to the plants themselves and can basically get better coverage and more information below the system. I think another sort of interesting thing to note is that even though these systems feel very different from autonomous vehicles, we can actually make a fair number of analogies between them. So if we think about the levels of autonomy in vehicles as defined by SAE, we basically can define these levels of autonomy by the requirement or what you need from the human driver. So if you need something like partial control, you need something like monitoring them and intervening when necessary, you can define basically this increase in levels as decreasing reliance on the human. And we can actually have a similar line or levels of autonomy for these field robots as well. So we can actually start mapping the same things from the autonomous system in the vehicle case to the agricultural robots. We can also think about this in terms of safety. And even though these smaller robots don't have the same sort of safety concerns as the autonomous vehicles, ag in general is actually surprisingly dangerous. So the number of fatalities in ag has actually remained constant for the past like 30 years. And it's actually one of the deadliest industries in the US. And pretty much all of the, or any reduction in ag has been primarily due to innovations in engineering that reduce the labor needs. So as we start developing these systems and reduce the reliance on basically putting people in these dangerous settings, we can actually have safety in a sort of broader sense, not necessarily specific to the agent itself. Okay, so to show this system, here is the small mobile robot that basically is meant to go up and down these roads and collect data about the system itself. So one thing that is important to note here is we have our system. It looks fairly autonomous and like it's working fairly well, but it actually has to be monitored by a human user as it's going. So even though it's pretty solid, it still needs this sort of babysitter. So we're not actually changing the need for new labor or reducing the labor costs. We're just sort of shifting what they do. And the reason why we need these babysitters is because even though these systems are fairly good and they're constantly getting better, they still do sort of run into weird cases where they just fail. And one of the big problems with these sorts of systems is these failures are really hard to classify, and they're actually very hard to detect themselves, just because there's so much that can happen within the environment itself. So to talk about these systems a little bit, so here's a front camera view of the sort of normal case. So as you can see, it's a really cluttered environment, and it's really hard to basically understand what's going on, even in the good cases. So what we did is we identified a few key failure cases that we can then use to basically try and correct and take into account some of these failures. So one of the really intuitive ones is a row collision. So this is where you collide with the side of the row. And I think one thing that's important to note is that even from just the front camera view, that looks fairly similar to some of the cases in the normal setting. We also have cases where we have untraversable obstacles. So this is a case where there's some obstacle or something in front of the agent itself that we cannot basically push through. And another case that we need to think about is the traversable obstacle case. So this is a case where there is something that is in front of the robot. So there's basically a piece of corn that's fallen here, where we maybe have some sort of obstacle, but we probably could get over it. Okay, so these are some sort of anomalous or failure cases that we have thought about or identified. But I think one of the interesting things to note about this is we have this problem where we have very few samples of these cases. We have lots of data in like the normal case. We have this sort of data imbalance problem. And even if we have a few examples of these different cases, it becomes very hard to characterize the failures themselves. So we only have a few examples and they're widely different. So we can't just sort of classify or state what sorts of failures they are. We need to build or lean into something else to give us some insights. So basically what we want to do is we want to start thinking about how we can formulate this failure identification problem as an anomaly detection problem. So basically, by using tools from anomaly detection, we are inherently considering some of these concerns with underrepresented or low probability events here. So we're recognizing that we can basically try and use this anomaly framework to identify normal or abnormal scenarios. So this would be basically normal or some sort of failure. And we can start sort of leaning into to then how to classify and identify the situations within that abnormal case. The other thing that's sort of nice about the fact that we do have these human supervisors is we can actually gather some small data set of labeled data based on human intervention. So we basically can find these failure cases while the human is monitoring or testing their robot. So we can get some samples and start to understand what's going on here in real time. And one of the nice things about this is once we have this failure identification, or we can start identifying anomalies, we can actually enable new types of interaction between the robot itself and its human supervisor. So we can start basically moving to the case where we no longer need the human to be there all the time, but we can just call them when needed and start thinking about different types of interaction there. And since I'm running a little bit low on time, I'll go a little bit quickly through this, but we've been working on thinking about ways we can come up with generative models to try and understand the environments in a more flexible way. So often in the robotics setting, we can think about failure anomaly detection as being similar or analogous to failure identification in the context of having very few samples or poorly represented cases. And often this takes the form of some sort of classifier. And this can be something as simple as a binary case where we have something like hypothesis testing, or it can be something more advanced, like a supervised multi-class system. So what we've been working on is thinking about ways we can develop generative models. So basically what we're trying to do is think about how we can take fairly high dimensional inputs and find lower dimensional representations that can help us better improve this detection. So if we can come up with a good way to basically reconstruct or generate these systems, we can have better detection. So basically what this will do is if we can have a really good understanding of the system in normal conditions or in normal places, we can then also improve the detection. Another thing to note here is, so we've been working on this idea of coming up with generative models here, but we also can have this multitask framework where we're both trying to regenerate the environment as well as identify what the failures are. And by having basically both of these competing objectives, we actually can improve the system overall by taking into account the errors and insights from both. So again, we want to basically be able to take these high dimensional inputs like the LiDAR from the system itself and be able to identify abnormal or normal conditions or identify the failure itself. And when we are executing our system, even though we're sort of building this generative model branch, we're really interested in basically trying to cast this problem as this anomaly detection framework, where we're just trying to identify basically what the system is. Okay, so one of the key things that we've been working on is basically trying to find this latent representation. So we basically want to find our representation of the environment itself and figure out what is most insightful here. And this is done again through this variational autoencoder framework here. And by looking at this system, or basically this latent or hidden representation here, we can actually get some insight to how we can start thinking about representing the environment. So by thinking about these hidden layers, we can basically start thinking about different representations or what insights we can get from the latent parameters. So for example, if we map these LiDAR to two hidden variables here, we can basically start thinking about, or we can start decoding this and understanding what the system is actually learning. And a few interesting things to note here is we have our first latent variable here And if we go through this, basically go down this axis here, we can see that this is basically trying to capture how open the area is in front of the LiDAR. So it's basically trying to capture whether or not there are obstacles nearby. And if we look at this other latent variable here, we're starting to understand sort of the swing of the system. So we can start thinking about whether or not it is sort of leaning to the right or leaning to the left. And we can loop this all together and get very high accuracy on the anomaly detection itself and pretty high accuracy on the failures themselves. Okay, so I know that was very quick, so let's go through some of the videos here. So basically what we're doing is we are monitoring this, the LiDAR streams and some of the states of the robot themselves. And we're basically trying to identify what sort of the scenario is and whether or not we need help from the human themselves. So you can get this to run in real time. We can see that for the most part, we have an overwhelming amount of normal cases. And eventually we can find some failures and identify these cases, which we can then close the loop on the system itself and use this insight to basically improve the overall system and hopefully help it get to the end of the field. So one of the common pieces of feedback that we get are whether or not this is a proper sort of anomaly case. But so to maybe show a true anomaly, here's a case where we have a true anomaly and a wild grad student will appear, and it will still be able to detect this as an obstacle and hopefully then fix itself or call for help as needed. Okay, so that's all I have for you today. So today we talked about many different failures in 3 different contexts. So in real world autonomous vehicle tests, in simulation, and in the case where we have these anomalous cases in the field. And hopefully some of the failures and insights will give you some inspiration or some use cases for basically how we can design more robust systems and try and capture these failures in a meaningful way so we can hopefully have improved systems that can both provide safety on the road and provide better coverage in the field. So I'd like to acknowledge all of my collaborators, both at Illinois and at Stanford. Our robots have been provided by EarthSense, and our autonomous vehicle is provided by Autonomous Stuff. And again, I'd like to thank all of my collaborators for this. So with that, thank you for having me and thank you for being a great audience. And I'll take some questions.
Thank you to you. It's amazing talk for this amazing talk, and there are already a lot of questions. I mean, okay, so there are many people with raising hands, and there are other questions on Slack. So let's start with the raising hands. So there is, you can talk, Muko Ped Yai. Can you say, yeah.
Yeah, in the beginning of the talk, you talked about a lack of models of perception uncertainty, right? So today we have Bayesian techniques that can output, uncertainty estimates for predictions, and there are other techniques as well. So why can't you use those kind of techniques and other explainable techniques for deciding when to intervene?
So is this for the in the very first few videos I showed?
Yes.
Yeah, so let me pull that video back up. Let me see if I can get it going. So, so you're actually right. And actually, when we were taking into account these issues, we were actually doing exactly that, where we can take some Bayesian approaches and use that confidence estimate to basically decide and tune whether or not we should be more conservative or not. But actually the problem in this case, and sorry, the system there, partially there. The issue actually wasn't necessarily with the detection system, but it was with tracking errors. And actually, even though we have some good Bayesian techniques to understand some of the uncertainty, recreating when and where these failures occur is still a challenge. So we basically had to put a fair amount of effort into thinking about in the tracking case. So when we say have a vehicle and we're trying to track it through the intersection and maintain its ID, so we can basically track where it is. We had to figure out ways to model basically how that tracking might drop and think about that. So it was more of tracking errors and coming up with a good simulation model for that. But as you mentioned, as we went to go fix some of the problems, we did start leaning into some of the uncertainty. But I still think there are some issues in just coming up with good representations, like finding when and why cases or perception systems fail. Yeah, I hope that at least kind of answered your question.
Okay, so there is another question from Manfred Morari. Can you please talk?
Yes, thank you. First of all, very nice talk, interesting problem, interesting results. The one thing I do not understand is your cornfield use case. And I don't understand it because the growth period of corn that you showed with all the difficulties, usually the farmer doesn't do anything. The farmer just watches the corn grow. Why would you want to drive through that cornfield?
Yeah, so that's a good question. So actually, farmers themselves don't necessarily walk out on there. They actually hire crop scouts to do it. So they actually, so they pay these crop scouts or these crop monitors to go out and basically test the field. And as you mentioned, this is not a sort of trivial task, right? These farms are huge, and you're not going to get good coverage of them specifically. So basically what they do is they hire these people that will go out and they will take a few measurements or sample a few things, and they'll report back to the farmers about the state of their field. But one of the motivations for this is, one, you can actually have better information and you should be able to have more sort of precise agriculture cases or help have more precise care for each crop. But you can also sort of enable new types of monitoring. So if you are able to get this information, you can have better ideas about what your yield is going to be, or you can do things like apply things like fertilizer or pesticides in a very sort of precise way. So the big motivation for this is to move away from the sort of spray and pray approach that we've been doing thus far. So as you have these sort of big systems that are just like spraying the whole field, it has significant impact on the environment and actually on the crops themselves. So by having these sort of deployed systems, you can have more precise things where you are sort of catering to what's actually happening and not just sort of doing blankets or field-wide applications for things.
I don't want to drive that too far, but at that time of growth, you do not apply any fertilizer or any.
I see.
But you do that when the corn is much smaller, and then many of the navigation problems that you have don't occur.
I see what you're saying. So you're right in that. So these systems can be applied through the whole time, and you are very right in that the failure cases are much less prevalent there. But we still do have these cases. But you are right that late in season we have significantly more intervention cases and whatnot than early season. And you do have better access to things like GPS. So yes, you are very right in that point.
Okay, so we have now a question from Slack from Gio. So can you talk, Gio? Can you say the question directly?
Sure. I had a couple of questions, but let me maybe ask one and then the other. So, so in your example for adversarial testing with pedestrian collisions, my question was, how do you specify the possible pedestrian dynamics? And more generally, how do you specify the dynamics of the adversary in your adversarial testing approach?
Can you repeat the second part of that question?
I think more generally, what is the form for the dynamics of the adversary? What do you use to specify that?
Yeah, so that's something that depends a little bit on your simulator itself. So in this case, we were using a very simple motion model that was basically based on acceleration. So basically just move according to some acceleration input. And it had very limited turning radius. So basically it was a very, very simple pedestrian model here. And that was actually one of the things that like leads to failure cases like, let's see if I can get it going. This case here, this worst case or adversarial example here, where you don't necessarily get normal behavioral, or I guess examples of normal behavior, because it's basically just treating this as a free form agent. And that's part of just the modeling assumption of the simulator itself. But that being said, you can, if you can add a more accurate pedestrian model here, the framework itself actually doesn't change. It just changes basically the simulation itself. And the area of being able to model pedestrian behaviors very well and accurately is a big area of research right now, and something that I think is really interesting. But in this case, it was a relatively simple model.
So just a quick follow-up. So how does the algorithm know that pedestrians don't generally start running towards a car and that they try to stay alive? I mean, how does it know that? Do you learn that from the data?
So in this case, we are not necessarily controlling that. Let me go back to this slide here, or actually let me go back one more. So in this case here, part of the ways to encourage you to find different failures is you can add these basically different weights or parameters to encourage different types of failures. So originally, when we were trying to find collision failures to help it find failures faster, we were actually trying to optimize or minimize the distance between agents. So we were trying to force collisions. And that's sort of what led to this sort of like a traction between the pedestrian and the autonomous vehicle itself. But as was noted, that's not actually a good insight. It's not, it's basically outweighing the probability model of just the agent itself. So depending on your model or your simulation of the system, it will basically determine how likely different actions are. So if you remove some of these heuristics and you just rely on the likelihood of actions, then basically you're falling back to how good is your simulation itself. And all of this does require having a very strong simulation aspect. To maybe circle back, I don't think this necessarily or directly answers that question. It does assume that you have a good simulator, which you don't. So if you don't have a good model of that pedestrian, then it'll only be as good as that model.
So I have a follow-up, but I'll take that on Slack so that some other people can ask questions. Yeah.
So there is another question on Slack from Rong Gu. Can you speak?
Yeah, sure. First, thank you for the talk. It's a very interesting talk. And actually, my question is quite general. So if you can give us, just some general understanding or your experience on this topic, it would be great. So when we consider the dynamics of the autonomous vehicles and moving obstacles, which could be nonlinear, how could we verify rather than just simulate the scenario of collision avoidance?
Oh, that's a good question. So I actually think, and I'm sure folks here can probably give just as much or more insight than I can. So I think if we have a good model of the system dynamics, I think there are lots of tools and lots of good work from both the verification community and the control community and having like robust and guaranteed controllers if we have good specified dynamics, right? I think one of the sort of open problems or big, I shouldn't say open problems, but one of the challenges is dealing with either the other agents or some things that are difficult to model. But for the dynamic system itself, I guess as was mentioned in some of like this original slide, this robust control, it basically gives you some guarantees on whether or not you'll be able to control the agent or the system effectively. And I think there are lots of tools like reachability and whatnot that can give you good guarantees on performance and safety for well-specified agents here.
Great,
Okay,
thanks.
so there is the last question from Dejan before ending the session.
So thanks first for your really fantastic talk, very inspiring. So my question is actually related to Rong's question. So you're focusing on adversarial testing, but in the end you want, when you put the car outside, to not to hit the pedestrians. And if you remain in the testing arena, what would be, in your opinion, the right notion of coverage that should be used for this scenario-based testing, where you would feel comfortable that you have tested enough?
That's a good question. And I think, so I don't think I have a concrete answer. And I think especially in the adversarial simulation cases, I think one of the big challenges is once you sort of have identified a failure and you're looking at the failures, it does become almost like a qualitative assessment or just sort of like a human decision part where you say, okay, I've found my most likely failures. Are these failures that I care about, or are these deal breakers? Is it not ready for deployment? And I think that's one of the sort of big challenges is you can always be safer. And I don't think it's going to be possible to eliminate these sorts of failures completely. So I think sort of moving or trying to figure out ways we can try and think about the designers and sort of how they make these decisions and what they value, I think is a good question. On the sort of human side, there are some design techniques that feel a little bit softer, but they do give you some frameworks to start thinking about different design choices and whatnot. So these frameworks are called value sensitive design, where you, once you have some empirical assessment of your system, you try and basically incorporate the stakeholders and users in. But I don't have a solid, concrete answer.
Okay, thank you very much.
Okay, so thank you again for the beautiful talk. Now we have, actually, we were supposed to have like a break, but I don't think that there is a lot of time. So in 4 minutes, we will have the next session that is a panel discussion on RV autonomy. So please go on the program and click on the Zoom link to participate.
Yes, and please come to this panel session. I think it will be very exciting, and Katie and 4 other panelists will discuss everything about runtime verification for autonomy. So stretch, have a sip of coffee, and yeah, please come in a couple of minutes to the other room.
Thank you very much. See you.
Thank you.